Welcome back to Grade 7 Math. We are now on chapter 4.2, and this is on Fibonacci sequence. It's a special type of sequence that was coined originally with Indian mathematics back in over 2,000 years ago, but it wasn't documented in Europe until a mathematician named Leonardo of Pisa, or Fibonacci, wrote about it in about the 1200s or so, and he used this sequence. He didn't invent it, he just used the sequence that was invented much earlier on, but it was found in his book that he wrote. The way we're going to look at it first is we'll look at the example that he proposed. And the example he proposed was this. We have a pair of rabbits, and these rabbits are baby rabbits, and these rabbits will only multiply, or they'll only give birth once they become an adult in 1 month. And every month, these adults will give birth to a new set of baby rabbits, which will then continue to multiply. And then he wanted to know how many baby rabbits, or how many rabbits in total, or pairs of rabbits there will be at the end of that first year. So what we'll look at is let's start with this sequence, and let's try to break it down and then write down the information that we can get from this problem. So let's start first with our first pair of rabbits. So on this side of the page, and this could be on your scrap paper in your notebook, you could start drawing all these rabbits down, and then we could just fill out the sheet on the other side of the page. So we'll start off in the first month. We'll call this January. We have 2 sets of baby rabbits, so we'll put a little b to represent baby rabbits. Baby rabbits can't give birth to any rabbits, so after the end of the first month, they are just still baby rabbits. Then they become adults as soon as we get to the second month. So in the second month, let me just put the month title here, and then we'll put the numbers of pairs of rabbits over here. So I have 1 pair of rabbits at the end of the first month. At the end of the second month, these baby rabbits become adult rabbits now. So now when they're adult rabbits, they're actually able to give birth. But at that second month, they haven't given birth yet because they just became adults. So we still have 1 pair of rabbits. In the third month, let's see what happens. Well, these rabbits still exist. They will actually never die. According to his theory, according to the situation, they'll never die. It's biologically impossible, but just for the purposes of mathematics, we'll say that they last forever. Zombie rabbits. Then we have, so these stay alive, but they'll also give birth to new baby rabbits. So in this third month, we now have 2 pairs of rabbits. In the fourth month, these rabbits are still alive. They also give birth to a new set of baby rabbits, and these baby rabbits now age and they become adult rabbits. So I have a total of 3 pairs of rabbits. Based on this, what's your prediction after the end of the 12th month? Well, let's continue on. I'm sure I'll run out of room, but we can look for a pattern if we can. In the 5th month now, these rabbits still exist, so they're still alive. These rabbits still exist. These rabbits on the left become adults now. But each of the adults also gives birth to a new pair of babies, baby rabbits. So now I have 3 pairs of adult rabbits and 2 new baby rabbits. So this is now a total of 5 pairs of rabbits. Let's just go 1 more month. So now the 6th month. If you can see a pattern, then we'll try to figure it out. Each one of the adults will have another baby, and all of the other pairs stay the same. So we have all of these 5 pairs will stay the same. So this stays the same, this stays the same, this stays the same. The babies become adults also. So these are my original 5 from the last month, but I'm now adding on the adult extra babies. So these give birth to babies, and more baby rabbits. So I have a total of 1, 2, 3, 4, 5, 6, 7, 8. I had 5 original pairs from the month before, and I add the 3 that were matured from the month before that. So I have 8. So if you notice, we had 5, and we added the 3 mature ones who also gave birth to new babies in that to make a total of 8. So in our 7th month, based on this pattern, we'll have 8 original babies plus the 5 that will have already matured from before. So these 5 are now matured. Those will continue, these will now make more babies. So the 5 plus the original 8 will now make a total of 13. And now we could start to see some patterns here. If we go back to these numbers, I see 1, 1, and 2. 1, 2, and 3. 2, 3, and 5. 3, 5, and 8. 5, 8, and 13. So if we look at this pattern, the sum of the 2 previous numbers gives the next number. So for the next month, for month 8, without having to draw it, I have 13 constant adults plus, 13 total originals plus the 8 new sets of babies, because those are the mature adults. So that makes a total of 21. For the 9th month, I'll have 21 plus the 13 is 34. For the 10th month, I'll have 21 plus 34 is 55. For the 11th month, I have 34 plus 55 is 89. And for the last month, the 12th month of the year, is 89 plus 55 is 144 pairs of rabbits at the end of that 1 year. So if you can see, this pattern grows with every step. So in filling out our chart, so now we have our terms. Our terms are basically any number that is found within this chart. So any number that is in a sequence. So a term is any number or item. Doesn't have to be numbers, could be colors or any other item in a sequence. So we have a bunch of terms here, and not other terms as well. The term that we are looking at that defines what category we're looking at is called the term number. And the term number is our independent variable. We decide what month we're going to be looking at. So in this case, our term number is what term are we on? And the term value, and you could just fill this in on the boxes that are on the side of your page. Term value means what value is that term. So for example, the term number for the month number 3, for the 3rd month, how many pairs of babies we have, pairs of rabbits, and we have 2 total pairs of rabbits, which means we decide the month we're going to look at. So we decide the 3rd month. That is the term number. We've decided the 3rd month. What changes is the number of pairs of rabbits in that month, and so that's dependent on the month that I choose. There are 2 pairs of rabbits in the 3rd month. So if we fill this out, all of our term numbers are all of these, the month. So the term number is actually our month. Whereas a term value is the number of pairs of rabbits. So we have our numbers down here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is our term numbers. And our term values are the actual number of pairs of rabbits that are found in each of those months. So let's just rewrite those very quickly. I'll just stop there. So this is our term number. Our term number represents what month we are on, or it represents what we decide on. It could be the figure number, it could be the time of day, but it's the number that we decide on. And what changes because of that is the numbers of pair of rabbits. In this case, this is the dependent variable. So I'll just write those very quickly. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. So this is the term value. Now what we're going to look at is what we call the down rule. Down rule means let's look at the patterns that exist within these patterns. So let's start with the term number. So that's the left side here. What's our down rule? Our down rule means what patterns do we see going from one number to the next. So if we start at the first number, start at 1, that's the first number we start, and then how do I get to the next number in this pattern? Well, it's a quite easy pattern because I'm just counting up. Normally, I'm counting up by ones. So I start at 1 and add 1 each time. So the down rule is start at 1 and add by 1 each time. A down rule for the other one, for the term values, is a little bit trickier. So this one is start at, oh, we kind of need two numbers. Start at 1 and 1, then, that's a semicolon. The term value equals the sum of the previous two term values. So which means I start at 1 and 1, and then the next term value is the sum of the two previous term values. So for the next one, I need to know the two values preceding it. So if I said, how many rabbits will there be in the 100th month, in 100 months from now, it's hard to know because I need to know the values of the 98th and the 99th month combined together. So sometimes the down rules are pretty easy to predict. Sometimes they're a little bit tricky. The Fibonacci sequence is a pretty tricky sequence in order to look for that. I'm going to show you a couple of other examples of where we see Fibonacci sequence in action. So here I have an image that's taken from Wikipedia, a couple of images. One of them you recognize. So what I have here is I have squares that have the dimensions of the Fibonacci sequence. So 1, then 1 makes 2. Then 2 plus 1 makes 3, 3 plus 5 makes, 2 plus 3 makes 5, 5 plus 3 makes 8, and 8 plus 5 will make 13, and it continues to spiral. And we'll, as you look in the video and we'll look in class at different examples of spiraling numbers and how they adhere to the Fibonacci sequence. As well, we looked at the Pascal's triangle. And if we look at the sum of the soft diagonals means the diagonal that's a little bit shallower than the regular diagonals that you could see within the second diagonal here. This means we're kind of cutting it a little bit shallower. And you notice the sums are in red. So 1, 1, 2, 3, if you follow along the red lines. 5, 8, 13, and if you notice, so the sums in the soft diagonals of Pascal's triangle are also the values of the Fibonacci sequence. So there's quite a few really cool things that are found in the Fibonacci sequence. We'll also be exploring this in class in grade 8 a lot more when we look at something called the golden ratio. So hopefully you understood this lesson, and take a look at the rabbits example again. Take a look, make sure you know the difference between term number and term value, and the new term, the new idea concept of the